Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where we're going to get ready to go back to school and help you get a head start in your calculus classroom. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make those tough to teach, tough to learn concepts accessible to all my students. I'm really excited to be joined by our two panelists tonight, Vicki Carter and Tom Dick. Vicki has been teaching high school math for 40 years and currently serves as the math department chairperson at West Florence High School. She's the former co-chair of the AP Calculus Test Development Committee and serves as a question leader at the AP Calculus reading. Vicki has served on TI-Nspire authoring teams and has presented at many international, national, and regional conferences in the areas of technology, calculus, and statistics. Vicki, thanks so much for joining us.
I'm so happy to be here tonight with everyone.
And Tom is a senior math advisor for Texas Instruments and is also professor and former chair of the math department of Oregon State University. He has served on the editorial panels for the Journal for Research in Mathematics Education and the Mathematics Teacher Educator. He remains active in the College Board's Advanced Placement Calculus program and has previously served as chair of the AP Calculus Test Development Committee. Tom, thanks for being with us tonight.
It's great to hear. It's great to be here with everyone.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send any questions to Vicki or Tom using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. Once the recording is available, we hope that's how you'll follow along. Don't try to follow step by step with what Tom and Vicki are doing tonight. They might be going a little bit too fast to try and do that, but the recording is the perfect place to do that. That way you can go at your own pace and then pause and rewind the recording as necessary. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate in the WebEx menu and choose Audio Broadcast. If that doesn't work, find your name in the participant window, and in that same window there will be a little phone icon, and if you click that phone icon, it will give you information to call in using your phone, and that should clear up any potential audio issues that you'll have tonight. At this point, Vicki is going to discuss our agenda.
All right, everyone, we've had our welcome and introductions. One of the first things we're going to do is discuss the four functions that you need to be able to do on your calculator that are allowed for the AP exam, and these are the things the students should be able to do with ease on their calculator. We're going to talk a little bit about what students should know before taking AP Calculus. The MPACs are part of the AP Calculus framework, and they have had, and this is a pun, I guess, an impact on what we're doing in calculus, and so we'll discuss those just a little bit. And then we're going to do some of those early calculus topics, exploring limits, doing some things with derivatives, talking about local linearity. The actual released AP question that we're going to look at is going to be part of the spotlight on the four calculator functionalities. So we'll look at that time, sort of early in the presentation, and then we'll have some information about online resources, and then there's the chance to win registration to the 2018 T-Cubed International Conference that Mike will tell you about at the end of the webinar.
Vicki, thanks so much. And Tom is going to discuss our expected outcomes for tonight.
Okay. And these were highlighted in the agenda also, but what we're hoping that folks come away with from tonight's webinar is certainly a refreshment or familiarity with exactly what are the calculator proficiencies that students are expected to have in AP Calculus, and get a glimpse at how to make use of that technology in powerful ways to explore these introductory topics of limits and derivatives that appear early on in the calculus course. And as Vicki mentioned, we'll get a glimpse of how released AP questions can really be used as a instructional tool in the classroom.
Thanks, Tom. Vicki, it's all yours.
Okay, so our first thing is to spotlight those 4 functions that students need to be able to do. And let me share my screen. Okay, and so this is a little document that I put together. We're going to look at each of those 4 functions, 4 things that students need to be able to do, but we're going to focus on the 2015 AB2 question that was on that released exam. This is the one that most of the students in the continental United States took in 2015. So the first function on the calculator that students should be able to do is to plot the graph of a function within an arbitrary viewing window. So on this particular AP question, students were simply told, let f and g be the functions defined by, and over on the right-hand side I have f of x, which is equal to 1 plus x plus e to the power of x squared minus 2x, and g of x is a polynomial function, x to the 4th minus 6.5 x squared plus 6x plus 2. And it then says, let R and S be the 2 regions enclosed by the graphs of F and G as shown in the figure. So this is actually a copy of the figure that was on the AP exam, and this is something that you can do on the Nspire, is actually insert an image. And so this is the image that the students were looking at. So they weren't told to plot the graphs of those 2 functions, but a student really should do that because there are several possibilities that will help them as they work through this question on the AP exam. One, have they entered the functions correctly? Because if they make a mistake, their graph won't look like the one that's on the paper. So it's a quick way to check and make sure that the correct notations were used. And for instance, the E there is the actual exponential E and not the letter E, because if they use the letter E, they will not get that graph. And then they can check how that, what they see on their calculator, how it corresponds to what's actually presented on the exam. Plus, once those functions are input in the calculator, whether this is an Nspire or a TI-84, they have use of those function names. So on the next window, I took the liberty of going ahead and putting those functions in and graphing them. And if you notice, this is sort of the standard window that comes up. Maybe the students would like to change the window so that it looks more like what they were seeing on the AP exam. There are a number of ways of changing the window. I'll go through the one that's probably the most intuitive, and that is to press the menu button, and you will see number 4 says Window, Zoom, and so we'll look at number 4, and then Window Settings, and sometimes people don't see it because it's the first one and it's highlighted, but Window Settings is what we want to go through, and so we get these prompts, and so if I look at, and I know you can't see it right now, but the graph was primarily in the first quadrant, so we might go from, I'm going to go from -1 just so I have a little margin there. So -1, and that rightmost point of intersection that was displayed was 2, 4, so I might go to 5. I can actually set my scale. Instead of letting the calculator do that for me, I might set it to be 1. My Y-min, I'm also just going to do -1. My Y-max, that upper Y-coordinate of that point of intersection was 4, so I think I'll go to 5. And then my Y-scale is a 1. And let's see what this new window looks like. And it's not exactly like what we saw on the exam. I'll go back. So this is what we saw on the exam. But I've got I'm very confident as a student at this point that I have put the correct graph into my calculator, or the correct functions into my calculator to get the correct graph. Okay, the second function. Tom, anything you want to add at that point?
No, that's fine. Yeah, looks good.
Okay. All right, so the second thing that students should be able to do is find the zeros of a function or zeros of functions, but that implies that they should be able to solve equations numerically. On this particular question, the students were to find the sum of the areas of the regions. Well, in order to do that, if we go back and look at that graph, you'll notice that the leftmost intersection point is given, as well as the rightmost, but what we don't know is the intersection point here. That would be a functionality students would be expected to be able to do. So let's look at how we will do this. I'll go to my graph screen. I'm going to go to Menu, and I'm going to go to Analyze Graph, which is number 6 there. And we're going to look at Intersection, which is number 4. And it gives me a prompt. It wants to know my lower bound. So I want to be to the left or have lower x values than the one of the point of intersection. So I'll select something like this. And then I want an upper bound, so I want a larger x value. And you'll notice that it's displaying the point of intersection. For those of you who are familiar with the AP exam, you know that these students need to report these decimals to 3 decimal places. So if I hover over this and then press the plus key, I can get more decimal places to display. A few weeks ago, some questions on the calculus community were about how to store this. I am going to show you how to do that. You may want to go back later and practice this. So if I click on this value, and then I go to Variable and Store Variable, it now says by default VAR. I would highly recommend selecting something other than the default VAR, something like A. And so when I input the A here and press Enter, that number actually turns bold, and that means the calculator now knows that it is stored, and in this case it's stored as the variable A, or it's linked to A. So it says, actually if I hover over it, it says linked equals A. All right, so let's look at the next functionality. So we've talked about the point of intersection. So the next one is that we can numerically calculate the derivative of a function. Now in this particular AP question, there was nothing about the slope of the tangent line. But I thought, oh, well that would be easy to do. So let's find the slope of the tangent line to the first function, which is f of x, at x equals 1.5. This will actually show you how we can use the fact that we input f of x as f1 of x. We can now call upon that as we find this derivative at a point, which is what the student is actually doing. So I am going to press the menu key. I could also go to the math templates. But let's drive everything tonight through the menu key. So we'll go to menu. Notice that there is a calculus menu, number 4, and there is a derivative at a point. So I'm going to go to the derivative at a point. And I get this box, and it says, well, what is your variable? Well, it is x. I can press the tab key, and now what value? I think I put 1.5, and we want a first derivative. So I'll say OK. I think the beauty of calculators now is the syntax that is being used. It actually prompts students to understand the syntax of proper notation and how to write, in this case, a derivative. So all I have to do is type F1. There is no special key, but notice that it went to kind of a bold look. That means the calculator knows F1, and I can put my of x in function notation and hit enter, and that would be the slope of the tangent line. The fourth function that students need to be able to do is numerically calculate the value of a definite integral. In that case, they are asked to find area, so that's a classic definite integral that they might have to find. let's just do one of those areas. I'm going to go back to the picture just a second. So let's do region R. So we need to integrate g of x minus f of x from 0 to A. That was our point of intersection. So I'll go back to my screen, and I need a calculator. Again, I will drive it through the menu. So menu, calculus, and in this case I want an integral. And we have a beautiful integral notation. My lower limit would be 0. I'm going to press the tab key. My upper limit will be A. It's stored, tab, and then it was g of x minus f of x. So I need to remember that g of x was actually f2 of x, and f of x is f1 of x, and I have to put with respect to x, or dx, press enter, and that would be the area of region R, and that would be calculating the value of the definite integral numerically. So that's on the Nspire. So Tom, I'm going to pause a minute and let you have a couple of comments while I go to the 84 so that we can sort of look at the same thing on the 84.
Yes, actually, before you leave the Nspire, Vicki, maybe you could do the following, and you can do it right here on this screen.
Okay.
You found the value A using the intersection key on the graphics. And that's not a feature necessarily one would find on every graphing calculator, but one of the features that would be some kind of solve command. And so if you could, you might just type in here solve.
Okay. Well, I went to menu. I tend to do menus to encourage students to know what's available to them. So I just went menu algebra solve. Okay. And we want
now
to
you could just type in f1 of x equals f2 of x.
And if I press enter now, it will tell me that I have a syntax
X, I think, but it may
yes,
take it just like it is.
No, I think we have to have our comma X.
So, because we're solving for X.
Yes. And so what we noticed
is
that we
here,
have
it actually gives all,
yep.
Oh, there's an intersection point that wasn't even on the screen, perhaps. I don't know.
That is correct.
Yeah.
Okay. Anything else?
But then still the graph is helpful in terms of thinking about which one of those is that point that was where the two curves crossed first.
Right. Yes.
Yeah. The one other point I would make, and this would go for either calculator, is if the exam question is really asking for area, and what you needed to find along the way was that intersection point. As Vicki said, the final answers on the AP exam are, if they're reported in decimal form, they're expected to be accurate to 3 decimal places. But what that means is if you're needing something like an intersection point kind of on the way to the right answer, you may want to incorporate more accuracy for that intermediary result to make sure your final answer is as accurate as could be. So here, using 4 digits here, I would think would be well worthwhile for that 1.0328.
Right, I agree. But storing it makes it even better because then it's retaining
stored more accurately.
Yes, yes.
Yeah.
All right, so let's look at the 84. I took the liberty of going ahead with the y equals key and inputting the 2 functions as I did with the Nspire. So if I press the graph button, basically I see, and by the way, the graph is a little bit slow. It's not really slow. It's just that it helped for me to already have them graphed, so they don't graph instantly like that. But these are the 2 graphs. Again, the window we were really looking at on the AP exam is this little window in here. So we could change our window in a similar way. we use the window button. And again, I think I put -1, and I'm going to drive this with the tab key. Actually, no, I'm not. I'm going to go, oh my goodness, what did I do? There, oh, I stepped back. I pressed something crazy. There we go back. Graph, window. Okay, now we're back. -1, click down here. Why does it keep doing that?
Did you hit the minus sign instead of the negative, perhaps?
Yeah, I need to be doing it. I think that's what I'm doing wrong. I was actually using the keyboard on the computer, and it didn't like that.
Oh, okay.
All right, so I think I did 5. And do the right negative. -1, 5. Okay, so let's look at the graph, and it should look similar to what we had on the Nspire a few minutes ago. So there's the one with the exponential piece in it. And then here comes the polynomial. And there's the first region R and the second region S. So we get a very similar graph. And intersection point, so let's find that. So that is under calculate. Notice that it's in blue. So we're going to have to do second trace. And we want intersection, which is number 5. And it asks us for first curve. And so I kind of like to always move this cursor a little bit. And so now I know I'm on the blue curve, so I press enter. And then it asks for second curve, and I can clearly see I'm on the red curve. I'll press enter. And then it wants a guess. And I like to get fairly close, although it should be okay somewhere along in there. And there we have our intersection point. Okay. And let's leave the graph screen. Hit the wrong button, I'm sorry. Okay, so now let's go to the math button, and let's do a derivative. So that's number 8. So the command is nderiv for numeric derivative. But notice that the notation is very similar to what we saw on the Nspire. So I put derivative with respect to x. Now that first function is y1. And if you look at your VARS, your stands for variables key, I need a y variable. So I'm going to go to the second column here. And I'm working with functions, so I want to use number 1 and a y1. And then I want this at x equals 1.5. And I press enter. And there's that slope. Let's calculate that integral. So I will go back to math. And the number 9, FNINT, function numeric integrator. And notice that we get a really nice integral sign now. Our lower bound was 0. Our upper bound, since we found that point of intersection, it was named x. I can actually use x. And then I think I had y2. So I'll go back and use the variables key. So I need y2 minus, and then I have to do it again, variables, y variables, function, y1. But I have to say dx and enter, and that was the area that we found on the Nspire. So those are the same things done on the 84 that we just did with the Nspire. Tom, anything?
Yeah, that looks great.
Okay. All right, the next thing that we were going to talk about for just a few minutes is what should students know before taking AP Calculus. So when Tom asked me this earlier, my statement was everything. But I do have a little list of things that I think are real important through the years that I have worked at the reading and with the AP committee and with my own students. A thorough knowledge of exponential and logarithmic functions is imperative with AP Calculus. A thorough knowledge of trigonometric functions. That includes the graphs of the trig functions, especially sine and cosine and tangent. Working with inverse trig functions and even having some working knowledge of those inverse trig graphs. Having some prior knowledge of limits really is beneficial if that can happen in, and I guess I'm calling it pre-calculus classes. It may not be named pre-calculus, and some of this could actually happen in algebra classes. I think it's also real important for students to be familiar with the calculator they're going to use before they reach calculus. The BC students need to have work with polar equations and a little bit with arithmetic and geometric sequences and series, and it really helps these students a lot if they've had some practice and opportunities to write explanations, the why, the justifications in courses prior to calculus. So that's kind of my collective list of things that are, to me, sometimes they come into calculus with gaps in knowledge, and that's kind of where they occur. We're going to talk real briefly about the MPACs, and I'm going to share with you a screen that Stephen Davis shared at the AP Annual Conference, which was about 2 weeks ago. And he was basically talking about how the mathematical practices for AP Calculus, which we have the acronym MPAC, the MPACs, had an impact on the reading. And the 6 MPACs, you can see them there, and they have bulleted items underneath them, and technology is in all of them. But MPACs 1, 5, and 6 was sort of a focus of things that we noticed as we went through the reading. So if you notice that number 1 is reasoning with definitions and theorems, there are a lot of Nspire activities and TI-84 activities that really get students to think about definitions and theorems and reasoning and writing about math, and that's important to do that with the students. Number 5 is building notational fluency. It's really exciting to see the calculators now have notations that are correct notations that will help these students build notational fluency. But they are very weak in writing notation. They're very sloppy. And then, of course, communication. So that's a really big one. I think, Tom, we probably need to go to our little exploring limits activity and then look at some of the other things. All right, so I'm going to go back to the Nspire. And this is a very simple activity. It's actually on the Math Inspired under Calculus. It's called Basic Limits. Students and teachers can explore here without having a lot of knowledge of how to input things into the calculator. So if you aren't very familiar with it, it's an easy document to use. So it says use the graph to answer the questions on the following page. So let's look at what those 2 questions are. And it says, what is the limit of f of x as x approaches 1 from the right? And then what is the limit as f of x approaches 1 from the left? So let's go back and see how could we use this TI-Nspire interactive document to explore this idea. So Tom kind of helped me talk through this a little bit. I think we want to grab this open dot and drag toward 1 from the left side. I think this kind of helps students understand this idea of approaching 1 from the left. So they're dragging from the left side. They get real confused because you're going to the right, but they have to understand they're to the left of 1. So what we need to observe is that that they have a coordinate for the dark closed-in circle. And so what we want to look is what's happening to the y-coordinate.
Something I tell my students, and this file really captures it, is I tell them to imagine there's a little person walking along the x-axis, and they're looking up at the graph, and they're taking a note of the function values. And what they're going to be asked to do is, okay, as you get closer and closer to that target of 1, you want to make a prediction of what the y value will be when you get there. You might be surprised when you get there, but you want to make a prediction. So that person walking in from the left, all they were seeing was the number 4 the whole time. So we would guess they would predict 4. A person coming in from the right is seeing numbers that look like they're getting, y values are getting smaller and smaller and smaller and approaching 0.
And there's just several, I mean, we'll look at a couple more. There's just several of these to get the students accustomed to dragging a point and thinking about these one-sided limits. So in this case, it looks like we're approaching -1 from the right and then approaching 0 from the left. And it seems so obvious to us that students really struggle with this concept at first. And so here, I think they are supposed to find the limit as x approaches 3 from the right and left. I think we have a pretty good idea of what we know is going to happen, but hopefully they'll take the time to sort of come in from the right and make an observation and then move over and then come in from the left and make an observation. It's a really simple document, and it's very easy to use, and I just think it really helps students visualize graphically what's going on with the limit. Do we have any questions we need to answer?
Hey, Vicki, there's actually been a couple questions that came up asking about storing a value on the 84.
Yes.
And if you say you find the intersection, if that value can be stored.
Yeah, well, I'm a little rusty on that. But I typically just found that one value from the graph that was called, let's see, I had it called X when I found it earlier, and I just used the X because that has always sort of worked until you need some other values.
Right. Students could also, I mean, it would be a little more laborious, but they could certainly store their own value.
Oh, yes. They could
as their own variable, right?
Yes. Yes. They can go to a screen. They could go here and do like 1.236 is, and then store that with this little button right here and pick a letter. So I have to do an alpha A and hit enter, and then it's stored as A. So that's very simple to do, and that is probably the easiest thing to do if they have multiple intersection points or multiple values that they want to store. But going back to something that Tom said, you would probably want to retain more decimal values than just the 3 I used. So you want more decimal values to store and then use that in your calculations. Does that help?
Yep. In fact, Michelle had chatted that once you find the intersection, if you just use the store button and then the second key minus, that automatically stores the answer's value.
Okay. All right.
So thanks, Michelle.
All right. Okay. Tom, do we want to go to our the one that you have with exploring a limit, sort of in a tabular kind of idea?
Well, that, or if you want, Vicki, why don't we go ahead and go back to the 84, and you can just, since you've just shown something on the Nspire, I could say a little bit about looking at limits graphically on just an 84, what you can do there. So what I'm going to have you do, I know I'm kind of doing this on the fly here, but if you go to let's see, y equals.
Okay.
And if you want to clear out your y1 and y2, and I'll just relate an anecdote. The very first time I ever used graphing calculators in my teaching was on this topic of limits, and I had no idea what would happen, and I was sold after the first day because of the reaction I had in terms of the way students were suddenly thinking about it. And all I did was use kind of my regular examples that I'd been using for years, but they really came alive in a different way using the graphing calculator. So this first function, let's try this, Vicki. How about the quantity x squared minus 1?
Am I making a fraction?
Parentheses.
Oh, in parentheses. Okay, x squared minus 1. Okay. Oh gosh, I don't have an X.
Something happened. Yeah.
I have a bad habit from Nspire of using my keyboard, and you can't.
Right.
I have a very bad habit. Okay.
So it's x squared minus 1, that quantity over the quantity x minus 1. So divided by the quantity x minus 1.
I did it right that time. Okay.
And
so
now before you graph that, if you could go to Zoom.
All right.
And do Zoom 4, the Zoom decimal.
Okay, the Zoom decimal. All right. And we have a nice hole in the graph.
And I'll never forget the first time I did this. I had students, these were those students from the back of the room that usually aren't paying attention. They were looking at their graphing calculators, and they were talking to each other, say, wait, my graph's got a hole in it. Does your graph have a hole in it? What's going on there? And I knew the hairs on the back of my neck stood up. So I thought, oh, I've got them. They're hooked. Okay, this is something we can discuss. What's going on here? And so is the pixel burned out? Well, we could try tracing and see what happens.
All right, so if I start there, I would be thinking about a limit from the left of 1.
So we can just trace along. And it looks like it's getting closer to 2. But when we actually get there, at x equals 1, there is no y value at all. It really is undefined. And what's nice is up at the top, we're reminded what function we put in. And sure, oh yeah, at x equals 1, that wouldn't be defined because we'd have 0 in the denominator. And coming in from the other side, well, yeah, again, for all intents and purposes, it looks like a line that has a hole at 1, 2, and that brings up the whole language of limits. And so this is a diagram for years I just drew on the board, but the difference was I always drew in the hole. Here, the graphing calculator draws in the hole, and that made a big difference. And that was suddenly this phenomenon that we wanted to discuss and figure out what was going on. Now, a little caveat here, if Vicki goes back to her window, and so if you press window, and all I'm going to have you do, Vicki, is just change the negative 6.6 to negative 6.5.
Okay, and graph?
And then graph again. Oops, no hole. And that's just something to keep in mind, is you're going to see that hole in the graph only if the location of the hole directly matches up with a pixel value. And that's why, if you pick examples where these things happen at integers, Zoom decimal is a great window to use because you're guaranteed every 10 pixels is a whole number. So here, if you were to trace, Vicki, you'll see why we don't see the hole. Notice the values, the x values, we're not actually hitting nice 0.1, 0.2, 0.3. We're now off a little bit. They're in equal increments, but it's this kind of odd decimal value. And so we're going to, when you go by x equal 1, so go ahead and increment up a bit. Okay, there's 0.84, 0.94, but the very next, you skipped over 1. And that's why we don't see the hole. So that's just something to keep in mind. If you really want to use the calculator to see that hole, you do need to kind of orchestrate your window a little bit to do that. I'll tell you what, go ahead back to Y1, if, your Y equals menu. And go ahead and change the numerator. You can leave the denominator alone. If you change the numerator to 1.
Just 1, okay.
Yeah, just 1 over x minus 1.
Trying to do it. Okay. Graph?
Yeah, there we go. That should work.
Do we want to zoom
and
anything?
Just go ahead and graph.
Okay, just graph. All right.
All right. So this is an example of a function that doesn't have a limit at x equals 1 because as we approach x equals 1 from the left and the right, we're getting the function values are growing either in the negative direction. They're growing in magnitude, but so from the left, we're getting these huge magnitude negative numbers. And from the right, we're getting these huge magnitude positive numbers. So that's an example of a limit that doesn't exist at x equal 1. Yeah.
And of course, somebody just mentioned that the table is real nice to look at too. So we could do
go ahead, take a look if you want to.
Graph and take a look at the table and actually see that error value there.
Right at 1, we have an error because it's undefined there.
Right.
Now here we would need to, our delta table is, we're not really getting real close to 1, so we might want to use a different delta table.
Right.
So let's see, we would need to do a table set, I think.
Okay. The delta table and try 0.1, or do we want to go smaller than that?
0.1 is probably good, and then you could, I'll tell you what, how about 0.05?
0.05, okay. Okay.
And since we want to approach 1, we might want to start our table a little closer to 1, say maybe at 0.75.
0.75, okay.
Yeah.
Okay. And so let's look at our table. There we go.
And here we still can see now numerically that kind of approaching from below or from the left. That's the 0.75, 0.8, 0.85. Those values are getting, x values getting closer to 1. And look at the corresponding y value. You can see how they're getting big negative numbers. Apologies if that sounds, when I say big there, I mean large magnitude, large in absolute value, but so more negative, right? And the opposite is happening as we come in from the right. So, there is kind of an interesting symmetry, though, isn't there, between these two? Yeah.
And students do need to be able to compute limits from tables, like looking at something like this and understanding, having a vision of what the graph is doing by looking at what the table's doing.
Right, yeah. Yeah, no, and that's this connecting across multiple representation is making sense. How does the graph tell us similar information to what this table and vice versa? Yeah, I think that's really powerful.
Yes. All right, you want to go back to
try one of my favorite functions next?
Yeah, or do you want to go to the Nspire and look at that interesting little document that you have?
Hey, the 84 is just fine. Let's just stick with it.
All right, we'll just play with the 84. Okay. All right, what's your next favorite function?
So on this one, let's just go ahead and clear out Y1. And this function, let's try the arctangent. You mentioned inverse trig functions.
Okay. Arctangent.
Yeah,
okay.
Arctangent of 1 over x.
Ah. Okay, you ready to?
And if you want to do a zoom decimal, why don't you do zoom decimal again?
Okay,
I'm not sure. We may not have. We're probably still on
Yeah, I
that
can't remember what window we were on, so.
Yeah. And what I like about this function is it's not one of those split formula functions, but it's showing actually the limit doesn't exist at x equals 0.
Right.
But it does have a finite left and right hand limit. So the left hand, let's try tracing and see what this looks like. Of course, when you first bring up the trace, it's undefined at x equals 0. We should have guessed that, but okay, so coming in from the right, it looks like it's getting close to somewhere around 1.5.
Yeah.
Let's see, is there any interesting value we might know that's close to 1.5? And it's negative 1.5 coming in from the left. The punchline here is it's actually pi over 2 from the right and negative pi over 2 from the left, but I'll leave it to our listeners to think about this function and why that makes sense, that those limits would be that way. So, and then finally, one more example, and it'll be easy to edit this one. Do y equals, just change that inverse tangent part to sine.
To just sine? Okay.
Regular sine. Yeah.
Right.
There we go.
Nice little graph.
And just graph that. Now, we already know, thinking about that formula, it won't be defined at x equals 0 because we have that 1 over x inside the parentheses. But it doesn't look too misbehaved. I mean, it looks like there's kind of a break there. It's hard to tell what's going on at x equals 0. So I'm going to ask Vicki to do the graphical equivalent of approaching 0 from both sides. And what that would be is if you go to your window, Vicki, I'm not going to have you change the y range, but I will have you change the x range by hand. So I want you to change the x min to negative 0.066. So I'm going to basically go in 100 times closer.
Okay.
And then x max would be positive 0.066.
Okay.
We're going to look at a very tiny interval around x equals 0. And we can see this function's just going crazy as we get close to 0.
Yeah.
Yeah. And again, this is something we can analyze and think about, but of course the regular sine function goes through cycles periodically over and over again. When we take the reciprocal of the argument, in other words, sine of 1 over x, as x gets close to 0, it's running through those cycles between -1 and 1 faster and faster and faster. So the closer you get to 0, the more this function bumps up and down. And so this is an example where it doesn't have a limit, but it's not because there's a vertical asymptote, not because there's a jump discontinuity, it's because the values are oscillating wildly. Just a quick thing, all the functions we looked at here, these are kind of standard examples that you find in textbooks. Well, maybe not the arctangent one, but to me, they just have so much more power when you use a graphing calculator like the 84 or TI-Nspire, just graphing and thinking about them.
Well, you can look at the graphs so much faster. I mean, you can, like we just did, we can switch the graphs and look at what's happening so rapidly and then talk about it, and you don't have to, sit and wait for something.
Right. exactly. Yeah.
All right, Mike, I think somebody wanted to look at a table on the Nspire. Is that what I kind of saw pop up there?
I think they were mentioning that with their students, they use the input value to set the ask, and that way students can type in their own values for X and discover what's going on with the limit, as I interpret that, what they're saying.
Oh, okay.
Yeah. Yeah, that's nice.
Yes, that's also a nice thing to do. Okay. Do we want to show that very quickly? Or, so if you go to table set and where it says independent, we would go down and put ask, and then we look at our table. Oops, hit the wrong button. No, I didn't. There we go. So now we input our own values. So like Tom, you said a few minutes ago, I don't know, we'll do.
So you might say, what happens at negative 0.001, something like that.
0.001, there we go. And 0.0001. And
notice how drastically different the value is. So.
Right.
So these are kind of bouncing all over the place because the sine of 1 over x is bouncing all over the place.
Right. So yes, and this is a very, that way your increment of x is not constantly 1 unit or 0.1 unit or 0.05 units. You can sort of narrow in on the x value that you're trying to approach in different kinds of increments, which, Tom, honestly leads to the thing that you do have set up, which might be a good little thing to look at very quickly and then put some closure to this. Yep. All right, so so Tom has this nice little document. So, Tom, I'll let you talk about it just a second. This might be the only example we can look at, but we'll look at it quickly.
Sure, yeah. So what this document is, it's not a real fancy program, but it's just to set up. You can define a function on the Nspire, and I've got a definition for the target point A. This is the point that X will approach. And the slider over there, what it will do is it will plug in values that approach A 10 times closer each time from both the left and the right. So right now, Vicki's got it set up to look at what's the limit as X approaches 0 of sine of X over X. So one click, we're now looking, well, what's the value of f of 0.1 and f of negative 0.1? And if she clicks it again, now it's 10 times closer to 1. And then she clicks it again, it will be 0.001 and negative 0.001. And so it's a way of kind of doing that geometric approach where you get 10 times closer. And it's pretty compelling evidence that this limit looks like it should be 1. Somebody asked about the table. Page 1.2 here, it has that same information in a list and spreadsheet page. So those are those same values in the table, so we can see the function values for some positive values approaching, positive values of X approaching 0, as well as in column C are some negative values approaching 0.
Okay.
Let's see. Maybe a final thing we could look at, Vicki, if you wanted to go back to the 84. Is, we've looked at limits numerically and graphically. Just kind of a final punchline here is as you get to the idea of derivative, let's just try plain old X squared here.
Zoom.
And zoom decimal would be fine, I think.
Zoom decimal.
Yeah, zoom decimal would be fine.
All right.
So we have a curve here, and what we're wondering about is how would we get a notion of what's the slope of that curve at, say, the point 1, 1. At x equal 1, x squared is 1. And for me, this is something that graphing calculators has just forever changed the way I think about derivatives graphically is instead of thinking about secant lines and tangent lines, what I'm going to ask Vicki to do is to just zoom in on that point 1, 1. So she's going to do a 2. And the first thing it'll do is let her move that point over to x equal 1, y equals 1.
I'll be there in a minute.
Yeah, no, that's all right.
All right.
And then when she hits enter, it's going to zoom in on that point. We still see the curve. And if she just hits enter again, it'll zoom in a second time. I still see a little bit of curvature there. And if you hit zoom again, repeatedly, maybe one more time. And now for all intents and purposes, at least visually, this looks very, very straight. And that's a very appealing notion, is that these kind of these smooth graphs, one of their features is when you look at them up close, they look very straight. And that's a very intuitive idea of what differentiability is about. Now, if we're looking at this straight line and we wondered what the slope of it was, the way we would normally do that is we'd pick 2 points and just figure out the difference in the y's over the difference in the x's. Well, Vicki's got 1 point right here. It's 1, 1. If she just traces 1 pixel over.
Oh, I went too many.
Oops, sorry. Well, I don't think you have trace on, maybe. Yeah.
Oh, I didn't. All right, but we're also running out of time, so this might be something they would want to explore on their own and play with a little bit.
Right, yeah.
All right. Let's see if I can do it really fast. So trace. Yeah, so you can see it's twice as much, the y coordinate?
Yes, yeah, the y values are changing almost exactly twice as much as the x values are. And so it looks like the slope of that line is almost exactly 2. And in fact, the more she would zoom in, the closer that would look like. And notice we didn't have to introduce secant lines or tangent lines. We're looking at the line. It's the close-up version. And that's that idea of local linearity that I think is really, really powerful. And that's a really nice way to introduce derivatives. I'm not saying you shouldn't still do secant lines and tangent lines, but for me, that's the way to introduce derivatives.
All
so
right,
it's probably
Mike,
time for us to turn it back over to Mike. Thank you all.
Thanks, guys. I appreciate it. As we wrap things up, I want to bring you to our website, education.ti.com, just to show you 2 quick things. On our website, if you look under the Professional Development tab, and you slide down to Webinars and Tutorials, in the middle are the on-demand webinars. So all the webinars that we've done recently and in the past have been recorded. And I was just looking at this as Vicki and Tom were presenting tonight. But for example, there's a calculus webinar that's been recorded, examining series using TI technology, another one on differential equations, applications of integrals, et cetera. So fundamental theorem of calc. So there's a lot of really good calculus-specific webinars that we've already done. They're recorded. Again, you can download the recording and all the documents and really go at your own pace. So this is, I think, a great webinar tonight to get me and hopefully all of you excited about going back to school soon and teaching some calculus. But if you'd like this and like some more additional material, this is a great way to do that. Also, under the Activities tab, if you go under Math Inspired and go under Calculus, and tonight we were exploring, for instance, some limits of functions. So I believe the file that Vicki and Tom used tonight was called Basic Limits, and someone asked, how do you find that file? So whenever you go under Basic Limits, you have access to all the student documents on the right-hand side, as well as teacher notes for that, and the TI-Nspire file. We're really excited that this year's T-Cubed International Conference is coming to San Antonio in early March. I really hope that you'll be able to join us, where you can meet Vicki and Tom and talk about calculus and TI-84 and TI-Nspire technology. We also mentioned earlier that we were giving away to one lucky winner a conference registration for the T-Cubed International Conference, and tonight's lucky winner is Ginger Ritchie. So Ginger, congratulations. We'll be in touch over the coming days here over email to give you a little more information, but we hope to see Ginger as well as everyone else at the T-Cubed International Conference. To receive a certificate of attendance, please go ahead and click the link in the chat window. That link contains the information about tonight's event, and the documents also contain, the links to the documents also contain the PowerPoint that I used as well as the material that Tom and Vicki had used tonight. So if you missed these links or they're not working for you at the present moment, have no fear, you'll automatically get a follow-up email in a couple days, and in that follow-up email will be a link to the recording, a link to the documents, and a link to the certificate. So thanks so much, everyone, for joining us. Tom, Vicki, thanks so much for everything you shared tonight. You got me energized to go back and teach some calculus, and hopefully everyone else too. So again, thanks so much, everyone. We hope to see you back online next week. Have a great night.
Thanks, everybody.
Thank you.